So I think I said that last time we were going to go into mutual inductance, but one more good three-phase problem here. So we'll look at this and then we'll switch gears to reviewing mutual inductance. I think we saw a problem like this similar to one of the sample exams, but still a good problem. We're told that we've got a three-phase system of two balanced delta loads. So sometimes just a real quick sketch can help you. So you've got a delta here. And those loads are undoubtedly going to be in parallel. So then we would have another delta. Like this. Okay, so something like that. That's what we've got going on. We're told that one is 5 ohms per phase, so each one of those boxes would be 5 ohms. One's 20 ohms per phase. Each one of those boxes would be 20 ohms. So I'll show you how to solve this a couple ways. Probably by far the fastest way to do this is to recognize that those two are in parallel. So you would have 5 ohms in parallel with 20 ohms, which by product over sum, 5 times 20 divided by 5 plus 20 gives you 4 ohms, right? Well, we could try it that way too. Okay. I don't know. Like I said, by far this is the fastest. May not be the cleanest. So now I've got something that looks like this, right? Where each one of these are 4 ohms. Okay. And we're told that the line voltage, the magnitude of the line voltage is 480. So for instance, across here, this is 480, right? Okay. So I could say that the current in the phase, I phase, that would be equal to the magnitude of that, is really going to be, because that 480 is just magnitude, so I'll just talk in magnitude because that's really all I want, is the magnitude of the line currents. What is the, let me say magnitude. Magnitudes of the line current. So I'm just going to say that's a voltage 480 divided by 4, which gives me 120 amps. Now that's certainly not the line current, that's this current in here. That's the I phase, isn't it? So I want this I line. So what's I line going to be, the magnitude of that? Should be root 3 times I phase. So we should come up with, what, 208 amps RMS. So that'd be the quick answer. If you're not comfortable with that, you could break it up a little differently. Just propose that we try Y. So let's give a Y a shot. So if I do a Y, what's the impedance Z for a Y is equal to Z delta. What do I do with the Z delta? Divide by 3. So I'm going to then have, for one of them I will have 5 over 3, and the other one I will have 20 over 3. Good so far? So I could say then that I had something like this, and I'm going to draw the single phase equivalent circuit. So I've got this in parallel with this. So this is the neutral down here, and we'll say maybe this is the A phase. We could take any of the phases. And this is then what, 20 over 3, and this is 5 over 3. So we could turn this into something that looked like this, right? Where I have the neutral and I have the A line here. So what's that going to end up being? I've got 1 over 5/3 plus 1 over 20/3. What's that? I bet it's 4/3, isn't it? Did that work out? Anyone try the math on that? Yep, I haven't made a mistake yet, so we're good. Now, the voltage across here, what's that going to be? Well, this is the line voltage, or line to line, right? So this voltage would be what? Have to be 480 divided by the square root of 3, wouldn't it? Yeah. So now if I want this current, I could say that that was I line, or I could say that it was I line. Couldn't I say that I have that I line is equal to voltage 480 divided by the square root of 3 divided by what, 4/3? Does that work out? Yeah, 208. Questions with that? So a couple ways to do this. Everyone's good with that? Okay. So, as promised, we'll look at mutual inductance. Usually I want to try and classify the problem. Is it an ideal problem where we're probably going to use this transformer sheet that we've used in the past? You remember that sheet like that? It's probably pretty hard to see there, but I think you get the idea of it. You still got that handout, right? You can bring that handout to the test as long as it doesn't have a bunch of writing on it. If you've written on yours, that's fine. Stop by. I'll be happy to give you a clean one. So, is this an ideal problem? Well, we're not given the turns ratio, are we? In fact, I don't think I gave you the mutual term. I should give you this term up here. Instead of giving you the turns ratio, I needed to say that this was J 1 ohm. So I didn't tell you that it was 2 to 1 or 1 to 3 or something like that. So probably not ideal. So I've got the mutual term there. So how do we then solve problems like this? Mesh analysis, right? Why don't I go ahead and take this as I1, and I'll go ahead and take this as I2. And we're looking for this voltage out there, so if I can come up with I2, I multiply I2 times 4 ohms, and I've got that voltage. Pretty straightforward. So looking at Kirchhoff's voltage law around for I1, using I1. Probably not a very good way to say that, but we're going around this thing. So we're going to have a gain of 24. So I'm going to say that's minus 24, or 24 at 0. And I'm going to add to that, we're going to take drops as positive, so I'll have a positive 2 times I1. And then I'm going to have another positive J2 times I1. Okay. So far, so good? And that would get me back to here. If I didn't have to worry about this silly mutual term, I would be done. I'd set that equal to 0, but I do have to worry about the silly mutual term in that this current I2 induces a voltage over here. And because I2 enters the dotted terminal, how's that voltage going to be induced in the primary? Positive at the dot, isn't it? And negative down here. So as I went around, I went from positive to negative. What's that? That's a drop. How do I treat drops? Positive. So I'm going to have positive J1 times I2 is equal to 0. Now I get to set that equal to 0 by Kirchhoff's law. Questions with that? So as nice as that equation is, it has two unknowns, I1 and I2. So what do we do? Kirchhoff's voltage law then for I2, right? So I start working my way around here. Maybe I'll start up here at that point, and we move around here. So I'll have 2 times I2 plus a minus J2 times I2 plus 4 times I2. And a lot of people would just say, well, that's 6 minus J2 quantity times I2. You could combine all of that. I guess I'd have one more I could put in there too, couldn't I? Plus J1 times I2. Have I got all the self terms okay? I think so. But there's a mutual term here, because this current here, I1, it's entering this dot, so it's going to induce voltage over here that is positive and negative like that, right? So as I go around there, I'm going to go from positive to negative. Going from positive to negative, that is a drop. How do I treat drops? Positive. I've chosen to take drops as positive, so it'll be positive. So it'll be positive J1 times I1. Kirchhoff says that's equal to 0, right? So you could reduce this, substitute if you wanted to, put it into a matrix, however you want to do that. Really what we're looking for is I2 out of this thing. Let me give you I1 and I2 as you maybe go through and try this on your own to practice. Should come up with 8.1 at minus 43 amps. And that would be just amps, not RMS. We were given volts, so this would be volts and amps. It's not RMS. Only three-phase do we take RMS unless noted otherwise. I2 is what we're really looking for, 1.3 at an angle of minus 123. And that's amps also. So that's the big deal, because then with that, I can say that V0, which I'm looking for, is equal to 4 ohms times I2, right? So when you run the numbers on that, you get 5.3 at an angle of, should be the same angle, minus 123, and that will be volts, not RMS. Okay? So that's one type of problem where the mutual term is given in phasor form. Okay? We're not given a turns ratio, so we're probably not going to use this sheet here. But those are coming. Questions? Okay. Well, let's try another type of problem. So we got this one here. Very different problem. Usually we think of an ideal transformer. It's probably going to have an iron core, so that'll be indicated there. It's got the dots. That's good. The biggest difference in the real giveaway is you have a turns ratio. We don't have any J business up there. We have a 1 to 2 or a 2 to 7 or whatever that ratio might be. So this one, we're definitely going to employ this sheet. You've got a similar notation in your book, but this sheet is nice and handy, so we'll go ahead and use that. So let's see how this comes out. We're told that this voltage here, V0, is 48 at 30, and we would like to find Vs. Working the problem backwards to find that source voltage Vs. So let's see if we can do that. Let's just put down what we know. You'll notice that I've assumed some currents in here. I've got I1, I've got this voltage V1, I've got this voltage V2. The voltage V1, that's going to represent the voltage drop or gain across this inductor, along with the mutual term from the current through this one. So it's going to represent not only the self term, but the mutual term. And likewise, V2 will represent the self-inductance because of current I2, but also the mutual inductance because of current I1. So let me just try and inventory what I know. I know that V0 is equal to 48 at 30 volts. Again, not RMS, just plain old volts. And that's going to be equal to what? Well, the voltage across there is the same as the voltage across there, so what could we call it? Call that V2, couldn't we? So there's V2 now. So I now have V2. Let's see. What if I wanted to talk about I2? How could I say I2? I2 would be equal to V0 divided by 24, wouldn't it? Which we could say would be equal to V2 over 24, which would be, when you make the substitution for V2, this turns out to be 2 at 30 amps. So that's kind of nice. We've got that one. I don't know that we were asked to find I2, but that should help. So now I need to essentially jump across this, this mutual interface and relate V1 to V2, because I know V2, and relate I1 to I2 because I know I2. Okay. So what I'm going to do, and this would be way too small to look at, but I'm assuming that you got this in your notes. If you don't have it in your notes, stop by my office. I think it's on the PDFs. I photocopied it in large form in the PDFs. But we'd go into this and we would find one of these that matched what we were doing, and we'd come up with the equations. We would eventually find one where V1 was equal to minus V2 over 2. And then for the current, we would be able to say that I1 was equal to minus 2 I2. Okay? And without the tables, I'm not really prepared to say whether those negative signs are legit or not. Or even whether I'm multiplying one by 2 or dividing the other one by 2. But when I look at both of these, if I look at both of these as a whole, I'm fairly encouraged because I'm dividing the voltage and I'm multiplying the current, right? If I was dividing both of them, that would seem wrong, wouldn't it? It would be really nice if we could have a transformer device where we could not only up the voltage, but up the current. We wouldn't need to finish lecture. We would all go get one. Okay? Doesn't happen that way. As I increase the current, I'm going to have a reduction in the voltage. So I see that ratio and it makes sense. Again, without looking at the table a little closer, I can't justify the negative signs. But you have a table, and you can go through that and justify that to yourself. So if we do this then, what do we have? V2, 48 at 30 divided by 2. So that gives me, I guess a negative sign, I didn't want to forget, minus 24 at 30. Volts. That's good. And what's this one end up looking like? Minus 2 times I2, which is 2 at 30, which is going to give me minus 4 at 30 amps. So we've got that. We've got V1 and I1. We've got everything but what we want. Vs. Well, what if we do a Kirchhoff's law? This is a little bit, I mean, we're kind of going at this backwards from the last problem, but that's okay. Kirchhoff's voltage law around the left loop, if you will. So what's that going to look like? I'm going to gain Vs, right? So I'll say my gain is Vs. And that's going to be equal to, what's that going to be equal to? The drops, right? So I have 6 times I1 minus J6 times I1. And then this V1, as I go from positive to negative, is it going that way? Is that a drop? That is, isn't it? Okay, so I could include that over here. So it'll be positive V1. So when I do that, I've got 6 minus J6 times I1, which is minus 4 at 30, plus V1, which is a minus 24 at 30, gets me, let me double check that. Yeah, that's right. 53, oops, 53.66. So 53.66 at an angle of minus 175.6, we'll just say minus 176. And that would be volts. Questions of that? Yes? my V1, right here?
Yeah.
Okay. That's the voltage across this. Yes. Well, V1 represents not only the inductance due to the inductance. I mean, if I gave you a problem like this, like we started out the term with, V1 represents its own voltage due to the inductance plus the mutual piece. Yeah. So it represents both those. Likewise, V2 represents its own voltage drop or gain plus the mutual piece. Yes. Good question. Other questions? So I try and keep my calculator out of the video here so this becomes timeless. A student already pointed out that my calculator is the same one that they have in the historical display downstairs. But anyway, so the good thing is you've got better on your calculator, right? We always come in on day one. I can do the problem in about 1 minute. It takes everyone about 10 minutes. And then at the end of the term, you're beating me. So that's good. That's the way it's supposed to be. Questions on that problem? Okay. Well, the last problem we have to do, we talked a little bit about this with the turns ratio. Where this is used is oftentimes impedance matching. So we look at a scenario where we have an amplifier driving a speaker, and they're different impedances, and we want to do impedance matching. A lot of times we use a transformer to do that. So we've got an 8 ohm speaker, and our amplifier says, no, 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 I want to drive something. I want the load to be 3.2 k ohms. So that's k ohms. Let's get that cleared up right now. 3,200 ohms. Okay. So what we want to do is we want to put a transformer in here. And if you've seen audio equipment, it's very common to have a transformer there driving the speaker. So we want to figure this out. Well, we talked about this during lecture, and I had something where I talked about this in general. We had this transformer, and we'll talk about the Zn. And we had this coupled to this coil, hence a transformer. And we talked about ZL here. Okay, and we said that this was turn 1, N1 to turn 2, like that. Okay. So we could say then, and we went through this before, but let's do it again. Zn is going to be equal to N1 over N2 squared times ZL. And I spent more time deriving that last time. But remember on this problem here that we just got done with, here we are dividing by the turns ratio. Here we're multiplying by the turns ratio. And when I look then at the ratio of the voltage to the current, we would expect that we would either be multiplying or dividing by that ratio squared, wouldn't we? So it should not surprise us that we see N1 over N2 squared. And like I said, I spent more time deriving that when we were talking about that in lecture. So I could say then that if you say that this is 1 to N, I could say that Zn is equal to, if I say N2 is 1, that's another good one, there's a 1. I could say that I have N to 1 squared times ZL, right? So how does this work in this problem? I say that my impedance or resistance in this case that the amplifier sees needs to be what? 3,200, right? So that has to equal then N squared times what the load is. What's the load? 8? Okay, so you solve that and N turns out to be equal to 20. So you're going to look at 20 to 1. Now that doesn't mean that this has 20 turns and that has 1 turn. That would be a very inefficient transformer. It'd be cheap to make, but inefficient. It's probably 20,000 to 1,000 or something like that. Maybe I need to change this a little bit. There we go. Okay, graphic artist here. Questions with that? Well, I think that's it for the review questions. So